Hello, and today we start our discussion for the first section for Chapter 2. We're going to talk about describing location in a distribution. So the goals here are we're going to measure position in percentiles. We're going to talk about cumulative relative frequency graphs. We're going to talk about position with respect to z-scores. We're going to talk about transforming data, density curves, and then describing density curves. All right, so let's get started. So percentile is the number that we assign as a distribution value where the p% of observations are less than it. So let's take an example. Below there is a stem plot of test scores from a test that Mr. Otten took, and Mr. Otten scored an 81. So let's figure out what percentile Mr. Otten's score represented. So the first thing we want to do is we want to count the number of scores. So we count total number of scores, and there are 25. And then we count the number of scores below Mr. Otten, so not including Mr. Otten's. So there are 25 scores total, and 14 of them are below Mr. Otten's. So then we use that value 14 over 25 to compute the percentile for Mr. Otten, which means that Mr. Otten scores at the 56th percentile. All right, so take a total count, figure out where Mr. Otten's score is, take a count of the scores below, use that for the numerator, total scores is denominator, and then you have your percentile score, all right, or your percentile rank. All right, so this brings us to classwork 2.1.1. Stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2019. So the key here is 5, 9. 5 with that slash up and down represents a team with 59 wins. So I want you to find the percentiles for the following. The Rockies with 92 wins, the Yankees with 103 wins, and the Indians with 65 wins. So I'm going to leave this up here for a moment, and then I am going to move on. All right, so next thing we want to talk about is cumulative relative frequency. So cumulative relative frequency is the accumulated relative frequency of occurrences. All right, so below is a list of the ages of U.S. presidents when they were inaugurated and the frequency of the occurrence. So I had 2 between 40 and 44, 7, not me personally, 7 between 45 and 49, 13 between 50 and 54, etc. All right, so now what we're going to do is we're going to take account of the total. We're going to see that we have 44 observations. So the first thing is to sum the frequencies, and then we're going to compute the relative frequency. So 2 out of 44, 7 out of 44, 13 out of 44, etc. corresponds to a certain percentage. And then we're going to add those cumulative relative frequencies. So 4.5 is the first, then we add 15.9 to that, brings us to 20.5, and then plus 29.5 brings us to 50, and then plus 27.3 brings us to 77.3, plus 15.9 brings us to 93.2, and plus 6.8 brings us to 100%. Sometimes you might end up with a cumulative relative frequency, depending on how many digits you're extending to, of plus or minus 100th of a percent. So it's not always going to be 100%, but should be very close. All right, so we're going to create a running total of the frequencies. This is a cumulative frequency, and then we're going to use that information to determine the cumulative relative frequency based on a given age. Okay, and then we can use that information to create a cumulative relative frequency graph where a certain age represents all of the frequencies of ages of presidents that came before. So this is 50 and below, 55 and below, 60 and below, etc. So once you get to an age where all of the presidents have been below, your cumulative relative frequency should be at 100%. All right, so this brings us to our next classwork problem, 2.1.2. Here is a list of the frequencies and cumulative relative frequencies of income. And so now, given that California has a median, and this is by state, I believe, or total, given that the median income for California citizens or households is $57,445, what percentile is California using this cumulative frequency chart or graph and the table? And then secondly, I want you to estimate and interpret the first quartile. So you can copy this down or pause this, and we're going to move on. Okay, so now let's talk about measuring z-scores. So z-score is a standardized value. It helps us determine how typical a value is based on its relation to the mean and a standard deviation. So z-score is some data point minus the mean divided by the standard deviation. So it really tells you how many standard deviations that data point is from the mean. All right, so let's take a look at our distribution with a stem and leaf plot. Back to the scores again. To the left is a stem plot from test scores. What's the z-score of Mr. Otten's score of 81 if the standard deviation is 6.07 and the mean is 80? All right, so you can take a moment here to calculate this, and then I'm going to give you the answer. So I'm going to take that value 81, right, the data point minus, and it has to be in this order because you can have positive and negative z-scores, and that's important. So please put the data point first, then subtract the mean, then divide by the standard deviation. All right, so this means that Mr. Otten's score of 81 is 0.165 standard deviations from the mean, and this z value will tell us what percent of the values are below or above 81. All right, so this brings us to our third classwork problem, I believe, 2.1.3. Oops. Sorry about that, 2.1.3. So in 2019, the mean number of wins in Major League Baseball was 81, with a standard deviation of 11.4. Find and interpret the z-scores for the following teams. New York Yankees with 103 wins, and the New York Mets with 70 wins. So I'm going to leave this up for a moment, and then we're going to move on. Okay, next thing we want to do is talk about transforming data. All right. So below is a scatter plot of data with guesses of the length of classroom in meters. So people guessed how long the classroom was. And this is a distribution scatter plot of the guesses of the classroom length in meters. So you can see here there are 44 guesses. The mean was 16.02. Standard deviation S sub x is 7.14. The min was 8. First quartile was 11. Median 15. Third quartile 17. Max is 40. Interquartile range is 6, and the range is 32. All right, so if we subtract 13 from each of these values, what happens to the characteristics of the graph? All right, so let's take a look at this, and let's see if you can work along with me. What happens to each of these values? And so I want you to pause for a moment and see what you think will happen if we subtract 13 from each of the values here. And I have the scatter plot posted above the original scatter plot. All right, so what happens? The number, nothing happens. The mean goes down. The standard deviation stays the same. Minimum goes down. Interquartile Q1 goes down. Median goes down. The third quartile goes down. The maximum number goes down. The interquartile range stays the same. So that width between first and third quartile is still the same, and the range stays the same. Okay. All right. So let's do another one. Let's add and subtract changes. So adding and subtracting changes measures of center and location. It changes measure of center and location, but it doesn't change the shape or the spread. So if I subtract values, it's going to change the center and location, but it doesn't change the shape and the spread. All right, so now if I multiply or divide, then what happens to the distribution? You can see it consolidates here. So going back through each of these, let's take a guess of what happens to the count, the mean, standard deviation, minimum, first quartile, median, third quartile, max, interquartile range, and range. All right, so you can see the count stays the same. The mean goes up. Standard deviation goes up. The minimum goes down. Actually, we multiply these out. So this is the first, and then this is the second one. The median goes up. The third quartile goes up. The maximum goes up. Interquartile range goes up, and the range goes up. So these values here now correspond to this bottom graph. Right? So these values correspond to error M here. And then we're saying if we multiply these values, what happens? These values are for error M. But if I were to evaluate with numbers error feet, then the mean would go up. Standard deviation would go up. This is not the value for error feet. Min would go down. First quartile down, etc. Okay, so when you're multiplying or dividing, it's going to change the location and spread, but not the shape. The shape generally stays the same, but the location and spread is going to change. All right, so this brings us to classwork 2.1.4. All right, so the dot plot below shows a distribution of heights from Mr. Otten's AP Stats class, along with a summary from the computer output. Suppose you convert the height from inches to centimeters, describe the effect on shape, center, and spread. Mr. A had everybody stand on a 6-inch platform and then had students remeasure from the floor. How will this change shape, center, and spread? And lastly, suppose you convert the class heights to z-scores. What would be the shape, center, and spread of the distribution? All right, so you're going to say if it goes up or down, or if it changes for each of these. So please stop, pause the video, and then come back after you've answered these questions. All right, so we're going to move on. We're going to talk about density curves and describing density curves. So characteristics of a density curve. A density curve is always on or above the horizontal axis, which means that all the values are going to be positive, at least from a y perspective. Second is it has an area of 1 beneath the curve. All right, so if you were to measure the total area beneath this curve, it would end up being equal to 1. And so what that would mean is that if you drew a marker here, then approximately 0.4 would be your area here, and 0.6 would be your area to the left. Or we can say 40% of the curve is to the right of this marker and 60% to the left. So the area under the curve and to the right or left describes now the proportion, which is what we're going to get at, of the observations that occur to the right or left of that value. All right, so when the mean and median are the same, then the distribution is symmetric. When it's skewed right, then it pulls the mean to the right, median stays the same. When it's skewed left, then it pulls the mean to the left of the median. So the median, again, is the point at which divides half of the area of the curve. And the mean is the balance point of the graph. Mean is pulled towards the tail. All right, classwork 2.1.5, your last one. Here's a density curve. Explain why this is a legitimate density curve, about what proportion of the observations lie between 7 and 8, and trace the density curve onto your paper and locate the approximate median. And then mark also the approximate location of the mean. So with a skewed density curve, you should be able to say where approximately the mean is in relation to the median, whether it's more towards the tail or not. All right, that brings us to the end of class. Thanks very much for joining. Please join us in our continuation of distributions in the next section.